So, you're already familiar with the world of computational fluid dynamics, or CFD. You've seen how this technology has played a crucial role from optimizing wing shapes to reducing drag in aircraft designs. However, like any tool, even it has its limitations, especially when it comes to dealing with highly turbulent airflow. Now, imagine an era dominated by quantum CFD. This advanced technology, although in its developmental stages, is bursting with immense potential. It has the power to solve intricate airflow problems at a speed much faster than classical computers, potentially leading to more precise simulations and even more efficient aircraft designs. But it's not all smooth sailing. With quantum CFD comes its own set of hurdles, from hardware constraints to the requirement for powerful error correction techniques. So, stay engaged as we delve deeper into the potentials and challenges of both classical and quantum CFD. Let's delve into the strengths and limitations of the renowned tool of aerodynamics, classical CFD. This established computational powerhouse has been our reliable ally in the field of aerodynamics for a considerable amount of time. Its popularity and widespread usage across engineering disciplines attest to its trustworthiness. The strength of classical CFD lies in its reliability and the ability to deliver simulations within manageable timeframes, especially when precision is the top priority and deadlines are fast approaching. What sets classical CFD apart, however, is its versatile applications. It's not solely about scrutinizing airflow over an aircraft wing. It's about refining wing shapes, minimizing drag, and even predicting the effects of atmospheric conditions on flight performance. From creating the fastest race cars to forecasting weather patterns, the applications of classical CFD span a broad spectrum. However, classical CFD does have its drawbacks, which can't be overlooked. When it comes to handling highly turbulent airflow, the complexity escalates quite a bit. Simulations become computationally expensive and time-consuming. The higher the turbulence, the more intricate the simulation. Moreover, as the complexity of the simulation increases, the approximations made during the discretization process can impact the accuracy of the results. To put it simply, breaking down a complex problem into more manageable parts can lead to a loss of finer details, resulting in minor discrepancies in the final results. While this might not sound significant in the world of aerodynamics, even the smallest error can yield significant consequences. Classical CFD, while an indispensable tool, does come with a set of challenges. It's important to remember that no tool is perfect, and classical CFD is not an exception. It's about understanding its strengths and limitations and deploying it judiciously to navigate the intricate world of fluid dynamics. After all, the effectiveness of a tool isn't just about the tool itself, but also about the expertise of the craftsman wielding it. As we delve deeper into quantum CFD's role in aerodynamics, its potential is nothing short of breathtaking. Imagine possessing the power to tackle multifaceted airflow dilemmas with an efficiency that far surpasses conventional computing capabilities. This is not a mere figment of our imagination, but a tangible reality, emerging with the advent of quantum computers. Their swift and precise simulations could enable engineers to devise aircraft with minimized drag and fuel consumption, crucial for efficiency and the ongoing battle against climate change. However, while the horizon looks promising, it's essential not to lose sight of the hurdles that lie ahead. Quantum computers, though remarkable, are not magical entities. These intricate systems, being in their nascent stages, require significant development before becoming an integral part of computational fluid dynamics, CFD. One of the most formidable challenges in this journey is error correction. Quantum computations are exceedingly sensitive, and the slightest interference might lead them astray. Hence, scientists across the globe are tirelessly working on developing methods to combat noise and augment the reliability of these sensitive calculations. Another obstacle is the challenge of scaling up. Constructing larger and more potent quantum computers is a task easier said than done. Nonetheless, strides in hardware design and fabrication are building the bridge towards this objective. And let's not overlook the necessity of algorithmic innovation. Fluid dynamics problems are complex, and we need specially designed quantum algorithms to conquer them. Fortunately, worldwide researchers are persistently exploring and refining these algorithms. While we acknowledge that the size limitations of current quantum computers and qubit susceptibility to errors present considerable challenges, we also recognize the essential role robust error correction techniques play in ensuring reliable quantum simulations. Quantum CFD's future in aerodynamics is filled with immense potential, but we must remember still in its early stages. As we embark on this journey into the unknown, it's crucial to tread carefully and responsibly, fully aware of the challenges that we must overcome to harness its full potential. But with great power comes great responsibility, and quantum CFD is no exception. As we venture into this new era of aerodynamics, it's vital to consider the ethical implications. One key concern is job displacement. The automation advancements in aircraft design could potentially lead to job losses. Navigating this transition responsibly requires careful planning and support for those affected. Then there's the potential for weaponization. As with any powerful technology, quantum aerodynamics could be misused without international cooperation and ethical frameworks in place. And let's not forget about our planet. The environmental impact of quantum technology's entire life cycle needs careful assessment. We must strive for sustainable practices in the development, use, and disposal of these systems. These ethical considerations remind us that we must navigate the future of aerodynamics responsibly. So where does this leave us in the world of aerodynamics? We've explored the established territory of classical CFD, a reliable workhorse for many engineers today. Its strength lies in its proven techniques and manageable timeframes. However, like all tools, it has its limitations, especially when tackling highly turbulent airflow. We've also peeked into the future with quantum CFD. Its potential is enormous, promising faster and more accurate simulations. Yet, we must remember it's not a magic solution. It's still in its infancy with challenges to overcome, from scaling up to improving reliability. But imagine this: a future where the reliability of classical CFD and the potential of quantum CFD work hand in hand. A future where we design more efficient, sustainable aircraft, all while considering the ethical implications of these advancements. The future of flight promises to be exciting, and the key to navigating it lies in collaboration and responsible innovation.